Okay, go ahead. What was the question about the
Okay,
procedure?
what does it, like if we did the 10 milliliters of ethanol and stearing, how could we do that at the same time?
To stir and add the ethanol at the same time?
Yeah.
Um, you just, I just do it like this. I would get some kind of stir rod. Let's see, stir rod here. And so what you're going to do is you're going to add the ethanol in the beaker. You just leave the beaker down there so you can stir it at the same time. Like this.
Okay.
That's to get the ethanol mixed in there rapidly. You know. But do we want to mix the ethanol rapidly? And so I'll leave that up to you. Maybe you want to mix it rapidly. Maybe you don't want to mix it rapidly. Let's try to understand something about crystals today. And so let's go through the steps. So we got all these steps, and so what we want to do is we want to look at the chemistry that's happening at each step. The report, somebody asked me about the report sheets for this. You're going to fill out the report sheets and turn that in. What we're going to do for this report, we aren't going to have this for all labs, but this lab is going to be a formal scientific report. And so what's involved? Well, the most important thing is what's happening, with the chemistry, which I'm going to talk about right now. And so basically what you do is you just try to, understand what we're talking about and then write it in your own words, what's happening chemically. And so what is happening chemically? What's happening chemically is, we're going to go through a synthesis, and in the synthesis, we're going to try to get some desired product. What is the desired product we're trying to get in the synthesis? The synthesis is going to be, somebody tell me the formula of what we're trying to achieve. The final product. This would be, if you go to like you see typically they'll ask you pre-lab questions. This would be a typical pre-lab question. Closed book, closed notes. What's the final product you're trying to synthesize in today's lab? Potassium. Oh, that's good. Name it, Scott. We'll go for it. All right, potassium. Synthesis of potassium. Trioxalate. Well, oxalate's the anion, so we never end it with the 8 or we have to drop the ending. So somebody help out. Okay, the first thing is it tri or tris? It's a bidentate ligand, so do we use tri or tris? Actually, we could use tri. The reason we could use tri is because the name of the ligand doesn't have, yeah, right. So, like tri, then you call it oxalate. Oxalate's the correct name for the anion, but when we name it as a ligand, we don't call it the same unless it's a neutral molecule. We would call it trioxalato, right? Trioxalato. What? Chromate 3. Chromate 3. Like this. Is that it? Dot 3 waters. So we could call it trihydrate. Let's just do that. Tri. hydrate. And so that's what we're after. We're after this potassium trioxalato 3 trihydrate, which is going to be a solid, liquid, or gas. It's a solid, right? We're trying to synthesize is a solid. That's important too. But it's got to be a solid if it's a hydrate, right? And so the formula for this is K3 square bracket here, and then we do the essential metal first, chromium, and then the oxalate. Oxalates, we get this abbreviation that we can use, OX for that. We got 3 of these, like this. And then we have the dot 3 H2O, and then the state of this is solid. Is that an ionic solid, a covalent network solid, or molecular solid? This is from Werner's discussion. Do you have it, Kelly?
The network solid.
A network ionic or a network covalent?
Ionic.
It's an ionic solid?
Network ionic solid.
Network ionic solid?
Yeah.
Yeah?
Yeah.
Yeah. Yeah, this is an ionic lattice. It would be a network of ions, you know, if you want to call it that. But this is ionic lattice. And it should form, you know, a crystal. You know, if you think about crystals, you know, there are a lot of different shapes of crystals that occur in nature, but really there are only 7 crystal systems. Did you know that? In Chem 1A, we only talked about 2 of the 7 crystal systems. The cubic and the hexagonal. Do you guys remember that? And then there's something called a Bravais lattice, you know. And the crystal systems are defined by the unit cell. Do you remember the unit cell? It's the building block of this brick. The Bravais lattices are how the atoms pack together in that building block. And so in cubic, there are 3 Bravais lattices. In the 7 crystal systems, there's altogether 14 Bravais lattices. But anyway, this is, I don't know what the crystal structure, I should probably look it up one of these days, but this stuff forms beautiful crystals. You can get them. You know, and so we're going to try to get, you know, high pure, because if you got a big crystal, you know, to grow a single crystal, it's got to be highly pure, because if there's impurities there, it screws up the lattice, right? Screws up the network. Screws up, and then they don't grow as big, right? And so usually, you know, when they grow those silicon wafers for chips, that's one single crystal, you know, high purity. They don't want defects in there, and then they shade it, a chunk off. And so we want to grow high. Well, obviously we want, you know, if you're going to make this stuff, you want to make it as pure as possible. Do you want a whole bunch of contaminants in this? No. And so when we're thinking about synthesis, we're always thinking about these types of things, you know, contamination. Well, anyway, we're going to start off. What are we going to make this from? Well, we're going to make this from potassium dichromate, right? And oxalic acid and potassium oxalate. And so let's take a look at the synthesis, the steps in the synthesis. And so we're going to break the reactions down. And so the first reaction is, you know, we're going to look at the potassium ions. Are they very reactive? No. And so basically what's going to happen is dichromate is an oxidizer. It's a great oxidizer. What does dichromate usually form when it oxidizes something? Chromium 3, right? Chromium 3. And does somebody have the chart? Because dichromate goes to chromium 3 is on the chart, right? And so this half reaction we can copy down, or if we know it goes to chromium 3, we can go ahead and balance it. What do you want to do? Should we just copy it down? All right, and so it's just going to be what? Plus 14H plus
6 electrons. 6 electrons.
Plus 6 electrons is going to yield 2 chromium 3s
7 water.
and 7 waters. After you see a pattern, you can balance these quite quickly in your head. Somebody was asking me if they could balance it in their head, but I said no because I want to see the work. All right, well, if dichromate, this is our oxidizer, right? It's a powerful oxidizer. And so what's going to be our reducer? Our reducer is oxalic acid. Oxalic acid is an example of a, what do they call them in organic chemistry? What do they call those things? Oxalic acid belongs to the functional group. You remember functional groups? You should have covered the alkene, the hydrocarbons, alkanes. You remember that? Alkenes, alkynes, and the alcohols, and the carboxylic acids. There you go. Carboxylic acids. That's it. Oxalic acid is an interesting carboxylic acid because it has 2 carboxylic acid functional groups back to back. You know, this is like a dicarboxylic acid, or 2. Well, anyway, if we were to oxidize oxalic acid, what would you guess? You know, this is a powerful oxidizer. So we are going to assume we're going to oxidize it all the way because we're reacting. I mean, this is way more powerful than O2 or whatever else, right? And so what do you think you're going to oxidize oxalic acid all the way to? Yeah, Kelly?
Carbon dioxide.
Carbon dioxide, right. Can you go beyond carbon dioxide? I'm thinking this is way powerful, so can we go beyond carbon dioxide? Not really. Not with an ordinary oxidizer. We'd have to have an exotic oxidizer, more powerful. Fluorine or something like that, you know. If you wanted to do that. We'd create some very unstable stuff. But is oxalic acid on the chart? Oxalic acid goes to CO2. Is that on the chart?
No.
No. So does that mean we ignore this one, or should we just... No, we need to figure out what's going to happen here. Can you figure out what's going to happen?
Appendix D.
Is it in Appendix D?
Yeah.
Oh. Bummer. It's a bummer because I wanted to go through this one, but you could have just copied it from Appendix D. Not everything's going to be Appendix D, and on the test, are you going to get Appendix D? No, you're going to get that, the little chart. The little chart can be good sometimes, you know. If you got a big chart like Appendix D, then you can make a lot of mistakes because you start questioning, you know, well, what's going on here? What's going on? You see lots of duplicate entries, but they aren't really duplicate. You know, if you want to understand redox a lot more, take a look at Appendix D rather than the little chart I gave you. Well, that's good, James. You saw that. It's on the chart, but alternatively, this is easy. We could figure out the balanced half reaction by using the skeleton redox method, which we balance the carbons first, let's say, by multiplying here. So we'll multiply by 2. Then what? Balance the hydrogens by doing what?
Excuse me? We do oxygen first.
No.
Oxygen's already balanced.
No, we don't do oxygen first. We don't do oxygen first because if we do oxygen and then carbon, it just screws it up again. We got to do the, we got to follow the sequence. We got to do the elements other than hydrogen and oxygen first. Try it. Try to do oxygen first and then see if it balances.
No, I mean oxygen before hydrogen.
Oh.
But never mind, the oxygen's
No.
already balanced.
Yeah. The oxygen is already balanced, so unfortunately I skipped that. How about that? I should have put it here. 4 oxygens, 4 oxygens. That's great. Okay, thank you. That's a problem. Sometimes, sometimes people end up skipping too many steps, and like I said, if I do it in my head, I will just skip all the steps and just go right to the answer, right? But then if you make a mistake, then you don't get much partial credit. And so even though the oxygens were already balanced, I should have written that down. Otherwise, if I made a mistake, I won't get as much partial credit. All right, then what? Charge. And so that's it. And then we just double check, 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, 4 oxygen, 4 oxygens, 0, and then plus 2 minus 2, 0. So it's balanced. And then what? We just add them up, right? Except there's a problem. We have to change it again. So this is 6 electrons being consumed, that's 2 electrons being produced, so multiply this one by 3. That works. And so the first reaction we're doing is dichromate plus 14H plus, and then the 6 electrons cancel, plus 3 oxalic acids yields 2 chromium 3 plus, plus 7 H2O liquid, plus 6 CO2, plus 6 H plus. CO2 is a gas. Everything else, except water, is AQ. So essentially what we're doing is we're converting the chromium from chromium 6 in dichromate to chromium 3 in the Cr3 plus ion. Is there a driving force for this? Yeah, there sure is. And so here's our oxidizer. Here's our reducer. Going backwards, what's our oxidizer, what's our reducer? Chromium 3 and what? And water. Actually, it really is just chromium 3, but we need the water there, otherwise, well, sometimes it's okay if it's missing, but certain things like this H plus, if this H plus are missing, then this doesn't work very well. If this H plus is missing, then what gets screwed up on the product side? If we didn't have H plus here, then you know how I knew that there were going to be 14 H pluses? I didn't even look at the chart. I automatically knew there were going to be 14 H pluses because I had 7 oxygens. It's a pattern you'll see when you look at the chart, right? You look at that chart, then it becomes. This is why some people said, "Can I balance it in my head?" Because they saw the pattern, and it's a pretty easy pattern to recognize, and they can balance it in their head. But anyway, and sure, if this was like a time test or something, then go for it. And you're sure you got it right, go for it. Because on like standardized tests, you don't have enough time to do all the questions. But this H plus is critical to form water, and so. If we don't have this H plus here, then dichromate doesn't behave like this. In fact, dichromate's a much weaker oxidizer if the H plus is not present. And that's because we aren't forming as stable of a product. We'd have to form some other product that's perhaps less stable. And so the oxidizer in this case is what? Well, this is, now I'm going to ask you, is the oxidizer CO2? You know, we need both. But let me ask you, in this combination, is CO2 the oxidizer, or is H plus the oxidizer, or is it a combination of CO2 and H plus taking electrons? Are both taking electrons? And so who is taking the electrons? Is CO2 the H plus, or both? Because we've seen H plus as an oxidizer many times. The H plus, you know, oxidizes aluminum, magnesium, a whole bunch of metals to form hydrogen gas. It's carbon. It's CO2. You know, see, it's kind of weird because CO2, you know, we'd expect H plus to be a better oxidizer than CO2, but in this case, CO2 would be the acting oxidizer. You know, because when I look at the chart, H plus, I would expect to be stronger. Anyway, what we got here is this. We already know it's stronger, stronger, weaker, weaker. How? Because a reaction occurs. Otherwise, if no reaction occurs, we're going to waste a lot of time mixing the dichromate. And so if you're already told the reaction occurs, or if you observe the reaction occurs, then there's got to be a driving force here. So this is a reaction.
When you cancel out the H plus at the end with the H plus,
No, we would cancel it out. Sometimes the H plus completely cancels out. If it completely cancels out, then it's okay. The reaction should still go, you know, even without it. But in this case, we're going to cancel. And so the H plus gets canceled there.
6.
And then this makes 6.
That makes 8.
Or 8.
Yeah, set it wrong. Did it right.
Okay, 8. Here we see it, you know, in the half reaction. Here, you know, well, the H plus canceled, but I'm not going to worry about it because, you know, it means I don't really need it. And the oxidizer is indeed
Carbon dioxide.
just carbon dioxide. But when we look at the half reaction, you're going, wait, don't I need that? Isn't that critical? No, it's not critical in this particular case because there's other source of hydrogen that's going to work out. Okay. In fact, water is going to be the other source of hydrogen. All right? So what kind of reaction is this? Redox. And so basically, in this redox reaction, what do you want as the limiting reagent? We also have to think, you know, ideally I'd like to do this stoichiometrically. You know, stoichiometrically means what in stoichiometry? If you do a reaction stoichiometrically, it means you add the exact amounts. And so I would add 1 mole of dichromate, 8 moles of H plus, 3 moles of oxalic acid, exactly. What do you think? Can you get that down to the nearest ion or molecule? Are you going to be able to weigh that out?
Not here.
It's impossible. And so when we do any kind of reaction, it's always a limiting reagent, excess reagent scenario. And so I want to ask you this because, you know, somebody asked me, should they do the pre-lab? Yeah, doing the pre-lab is always good, but the pre-lab is going to screw you up for this one in the limiting reactant calculation because of how they wrote the reaction. You know, this is why I'm writing all the reactions on the board. A lot of people don't copy this and then they show me the reaction they have in the manual. It's wrong in a way. But what would you have as the limiting reagent? What would you have as the excess reagent?
let me use wouldn't it be that?
Yeah, you want it to react because the CO2 and water is...
Yeah, the limiting reactant better be the dichromate. Because do you want dichromate left over? No. Oxalic acid, no problem. We could have leftover oxalic acid. In fact, that leftover oxalic acid is important for the next step. What are we doing in the next step? So we know we have excess oxalic acid, right? This is excess. And the LR is this. Normally with the excess, you know, excess reagents end up contaminating stuff. You know, like, I don't know if you guys did the sulfate lab.
Uh-huh.
Excess barium chloride ends up contaminating your barium sulfate. How did you get rid of that? Because you added excess barium chloride because you wanted the sulfate to be the limiting reagent. So how did you get rid of the excess barium chloride?
Filter,
Hmm?
filter it.
You filtered it? That gets rid of a lot of it, but not all of it. Because some residue might be stuck on the surface of the barium sulfate crystals. So how did you get rid of it? You rinsed it, right? You rinsed off the crystals. That's correct. So in this case, do we have any crystals we can rinse off? You know, what are we going to do with this excess oxalic? How are we going to get rid of it? Do we have to get rid of it? Should we get rid of the excess oxalic acid? No, we're not going to get rid of the excess oxalic acid because we might be able to use it in the next step. What is the next step? We're going to add
Yeah, potassium.
We're going to add potassium oxalate. What's that going to do? What is the potassium oxalate acting as? What do you guess? A ligand, right?
Ligand.
A ligand. Oh, why don't you write the reaction for this? I'll give you a couple of minutes. You write the reaction for this next step. Tell me what's going to happen when you